Okay, this is a problem about springs, and in particular about oscillating springs. So we started with a vertical spring of spring constant K and a mass M. So there's really sort of a prelude that starts this problem, and that is that if we put the mass on and let go, when it's in equilibrium, the spring will still be stretched. So the sum of the forces in equilibrium will be zero, and we can call this the upward force due to the spring minus the gravitational force downward. And really, we can call this x naught because this is how the system would be in equilibrium, just at rest all the time. And so we find that k x naught is maybe obviously equal to the weight of the object. Okay, then what we do is let's imagine that if, since we've defined gravity as downward, let's call this the upward direction as positive. Okay, so if we then move the mass upward by some distance, then that means that now we have a new set of forces. We have the k x naught, and now plus a new x, but since that was in the upward direction, let's see, so if we add a new x, this is going to be subtracted from the original hang length. And now this is going to be also with mg, but now it's not zero. Now the thing's actually going to accelerate if we push it upward and let go. So I'm going to write the acceleration immediately as the derivative because that's where we're headed. So I distribute through and I find that kx naught minus kx minus mg is equal to m times the derivative. So I know from the first part that these two cancel out, and what I'm left with is minus kx is m d squared x dt squared. So anytime we can write something that looks like a minus sign, something, set of constants, anything really, that goes in a box, times x, when that's equal to the second time derivative of that thing, this is simple harmonic motion. And we know that the solution to this problem is always some kind of sine or cosine wave. And if you plug my solution back in, you'll find that it works if and only if k over m is also equal to omega squared. So that means that omega, the angular frequency for this system, is square root of k over m. Remember, it's not actually going around in a circle. This is just the frequency of the oscillations in cycles, but instead of cycles in 2 pi radians. So if you wanted to find the period of the oscillation, the period is 1 over the frequency in cycles per second. So that means, let's see, then this is 1 over omega, but omega's in cycles per second. So it's not 1, it's actually 2 pi. There we go. So it's 2 pi times the square root of m over k. And now we can check and think about that. If we have a heavier mass, we get a longer period, and if we have a stiffer spring, we get a shorter period. And so that works. We're done.